Thank you for the introduction and for the invitation. And yeah, today I would be talking about recommendation systems. So from clicks to care, basically I will try to talk a bit more about technical or computational methods and a brief introduction into recommendation systems, and in light of my own research from the past few years and what we do recently in terms of recommendation in supporting mental well-being. So I was told that, but before I start, how much time do I have, just to be sure?
We are here until 1:15, so I mean, it's up to you for your presentation.
Okay.
Yes.
Okay, so I'll try to do like 30, 45 minutes maximum, and then I will leave some time for questions maybe. Is that okay?
Yes, that sounds great.
All right, so yeah, let me start. So, well, as you all know today, we are creating more data. Thanks to the tools that we have, our options on the web are really limitless. So we have really powerful tools today, LLMs, AI tools that allow us to create more interactive platforms and tools, which allow us again to create more content, which can be used again to create more powerful tools. So it's an interesting loop that we have, and this is a rather old statistics that I'm presenting here, which tells us that how much data that we are creating. So every year we are actually creating more data than the entire history of human history. So yeah, this is a great thing. So with this abundance, we have more powerful tools, but this abundance actually creates a lot of problems. Yeah, as you can imagine, we have a lot of options, which is not necessarily a great thing because we suffer from a fear of missing out, or FOMO. So how do we know which choice is the best? Or after we select something, then how can we make sure that we have made the right choice? So as you can imagine, today we have a lot of service providers for almost every product or service we try to consume, and decision making has become extremely challenging. So in an ideal world, what we want to have is actually, it's great to have abundance, multiple options for the same service. But on one hand, we also want to preserve this certainty of the decisions that we take. So the kind of services that we consume. So in an ideal world, we want to maintain these two. And this is actually where recommender systems come in. They try to help us basically solve the problem that we created ourselves. So the bigger picture, personalization is like an umbrella term which not only refers to recommendation, but it also captures the bigger picture of adaptation to human needs. But personal recommender systems are like subclasses of personalization. So particularly they refer to algorithms or systems that help us find things that we might potentially like. So this essentially refers to decision-making problems. So what products to consume, movies, news, all of these typical things that you use on social media, recommendations are all basically derived from recommender systems. So for example, I think this is a little bit old statistics, but 80% of content, for example, consumed on Netflix is attributed to their recommender system. The same on YouTube and Amazon. So they are really powerful tools that allow us to find things that we could potentially benefit from. So if we kind of look at how they work from the classical machine learning approach, so we have data, we have the machine learning models that use these inputs, and then try to make some predictions. So in the case of recommender systems, the data is basically user preferences. So you have explicit feedback or implicit feedback. For example, if you like something, or if you don't like it, or if you give a star rating system, or an implicit way of collecting this is, for example, based on your interactions indirectly. So for example, if you purchased something in the past, or if you watched a certain movie, or if you read a book, this kind of information can be used. And the recommender systems are basically the algorithm that take this as an input go through all the available content and try to predict our future behavior. For example, what books we might be interested in based on what we liked, or based on the star rating that we give for a certain item, what would be interesting for us in the future to consume. So in literature, there are like three schools of thoughts or three kinds of Rex's approach. So the first is collaborative filtering. So this is basically based on the analogy of similar users like similar things. So users could be subscribers, they could be readers, buyers, and customers who also bought this item. Do you remember this quote, a famous quote from Amazon, for example? When you go on your Amazon, you can see customers who also bought this item also bought the following items. So this is also a recommendation. So the central assumption is similar users like similar things. So for this kind of approach, the data is basically user and item interaction. So this is basically could be a rating, the amount of time users spent on a platform, or it could be a click-through rate. So something that is interesting in collaborative filtering is when you have a new item, for example, nobody have interacted with it, or when you have a new user who hasn't already given their preference to any of the items that we have in the database. So this is something called a cold start problem. So you have a new user, you have a new item, so recommendation is not possible in this case. So this is a common challenge in collaborative filtering approach. The second technique is what we call content-based. So this approach works based on the comparison analogy, basically between user profiles and the contents. So for example, users at the age of, I don't know, like 19 to 35 would be interested in action movies. So this suffers less from cold start problem because we already have these kind of assumptions that users are in a certain category, and a certain category can actually be interested in some features or specific aspects of a content. And the last one, or the third common approach, is a combination of these two. For example, it could be a neural network that takes both the user and item properties and try to predict future behaviors or items that can be consumed by users. And more recently, there are also some approaches like multi-stakeholder aware, which takes into account not only what users might be interested in, but also other relevant stakeholders that have a saying in the platform or in the service that these recommendation systems are being deployed. And also LLMs, as you know, are also being as recommendation system techniques. For example, zero shot and few shot techniques, without even knowing much about the users, they try to give some kind of recommendation. So, but today I will be talking more about content-based recommendation, as most of my research work in the past revolves around content-based approach. So the first thing I would like to start talking about is personalization in museums or in visual art context. So I don't know how many of you have been in the National Gallery of London before. I start this part, just a quick disclaimer, most of the content that you see here is part of the cross-cult knowledge base. This was a Horizon 2020 project. I was involved in an extension of this project to build some recommendation systems. So just to let you know, most of the content that you will see around this topic are taken from the cross-cult knowledge base. All right, so museums are essentially what we call cyber, physical, and social system. I'm not sure if most of you or how many of you are familiar with the concept of cyber, physical, and social systems. So as the name suggests, there is a cyber component, there is a physical component, and there is a social component, which is also called for short CPSS. So in short, this is basically system or a smart environment where humans and the cyber physical systems or the smartphones, could be robots, could be screens, cameras, different things cohabit and interact both virtually and physically. So museums can be seen as cyber physical and social systems. So we have points of interest, which are paintings, for example, and we have users carrying their sensor-enabled smart devices, and we have also some other devices, like could be sensors in the museum, which are cyber physical systems, which are a compute, and we have a physical component, and they interact together in the same physical space. So the task here is essentially, okay, we want to give a recommendation for visitors. Think of a museum that you know, for example, National Gallery of London, which is quite big in this case, which is around 46,000 square feet across 3 floors. And users usually come in for a day if they have enough time. But maybe sometimes you show up for 1 hour of visit, and there are thousands of contents across 3 floors. And they need to have some kind of personalization to help them find the right items that they would be interested in. And then after, you need to help them actually find those items across these huge museums. So the first challenge is basically finding those interesting items, basically recommending visual art. So it could be implemented through a mobile app or a VR glass or a mixed reality glass. But the task is finding those interesting paintings. Okay, so this means you have a painting or an item that the user might have liked. Okay, I like this painting. I gave it 5 stars. So the personalizer essentially needs to find those similar paintings that are close to what the user liked. So this means we need some kind of model that learns or that has a good understanding or a good representation of this data, the content basically. So what is a good representation then? A good representation essentially should capture these nuances or similarities between the content, and from this we can drive similarity metrics so that we can give basically a ranked list of recommendations. So let's talk a little bit about good representation. What does it actually mean to have a good representation? So let's take a look at an example. What would be a good representation of this image? What would you say a good representation of this image? For example, if I say a dog, which is basically 3 letters, kind of summarizes these thousands of pixels of an image into just 3 letters, right? And after I kind of make a representation of this image, what if I ask a question, okay, is this dog mine? Looking at only the image, I can say, yes, this is my dog. Or looking at only the representation without looking at actually the image, I cannot answer this question because it kind of loses some important information. It summarizes the image, which is thousands of pixels, into just 3 letters, but it kind of loses something. What if I ask, what is the dog doing? Looking at the image, you can actually answer, if the dog is resting or sitting or if he is running. But looking at only the representation, you kind of have a hard time figuring out. It's just the letter dog. You have no idea what the dog is doing. What if I say, is the dog safe? So this kind of gives us an idea of what kind of information we try to preserve, or when we try to represent or learn a representation. There is too much information loss here, right? So what if I do German Shepherd dog resting on a floor in a living room? This is a bit descriptive, right? Without looking at the image, we can actually answer some interesting questions like, what is the dog doing? Is resting? What kind of dog is it? It's a German Shepherd dog. So we want a representation which is a summary of an input, but it should also be a bit more descriptive. So when we think about representing items or images, paintings in computers basically get numbers. These are like very high dimensional vectors. And the representation is also going to be a vector, which kind of encodes some kind of semantics across each dimension. For example, the first dimension could capture something about the shape of the ear, the color of the skin. So different semantic components can be embedded in different dimensions across these embeddings. So if we look at how this kind of evolved from the traditional machine learning or information retrieval, in the beginning, people were trying to learn a classifier directly from input data, meaning we have a very high dimensional vector, for example, trying to classify cats and dogs. It looks like a very trivial problem today, but in the beginning, in the 90s, it was a very challenging problem. So you were trying to basically learn a classifier from an input data which has a lot of redundancy. So it was very difficult to actually solve this problem because there is a lot of redundancy. The features that distinguish cats from dogs were quite hard to capture. So what people started doing after this was, okay, we should try to actually summarize what is relevant for each of these components or for each of these items and summarize those features out. And basically try to learn a classifier from this. This is what we know today, dimensionality reduction. So handcrafted features. So we extract whatever we think is relevant to characterize a cat and a dog, and then we extract and summarize these features, and then we try to learn a classifier, basically. So it kind of performs a little bit better, but it didn't really nail the task. So fast forward with the arrival of deep learning frameworks or into neural networks, we no longer have to work with actually this predefined set of features. Instead, we learn features directly from the data based on the task. So meaning whatever features are good or relevant to improve the accuracy of the model, they will be basically summarized and extracted out for us. So we managed to achieve superhuman performance with neural networks or CNNs particularly. So this was great. So now we can learn features from inputs that are really useful, but can we learn features that are useful also for other tasks? Meaning now, can we learn transferable skills? And people started to ask these kind of questions. Like, for example, can we learn a representation of cats and dogs on which we can solve one task, which is basically, can the neural network tell if it's a cat or a dog? But can it also be useful to detect, for example, if the cat is sick? What kind of breed is it? Sometimes we don't even know what kind of task we want to engage these representations. So this kind of led to the emergence of learning representations. And there is a whole field of machine learning called representation learning. There is even a conference, I'm sure most of you know, ArtAICare. So people try to kind of design optimization or objective functions which try to encourage these kind of properties to learn features that are more general and useful. So to summarize, what we actually want to learn is a good representation. What does it mean? This essentially means we want it to be low dimensional, meaning a summary, and we want it to be reusable across tasks, not just for the task we want to solve, but it should be kind of useful to solve even future tasks. Sometimes we don't even know what these tasks are in the future we want to solve. And we also want these representations to be smooth and spatially coherent. This essentially means, for example, if you look at this representation of the MNIST dataset, you could tell that this is a good cluster or a good representation. So the feature extractor did a good job at actually segregating them or separating similar numbers or similar items close to one another. So when you use or search this space for retrieval or for recommendation, you have a smooth transition between similar items. And the last property that we want is essentially, we want them to be disentangled. This has a lot to do how data is structured in the latent space. So for example, if you play with the color a bit in the dimension where colors are represented, it should not really affect the dimension where you have other semantic properties. So representation learning or good representation essentially should have this kind of properties. So now let's come back to actually the task of art recommendation. So in the early days, people were trying to use metadata, basically manually curated representations to drive recommendation, like authorship, history, different kinds of metadata information. For example, if you like painting by Picasso, I can give you a recommendation of what Picasso did. But this kind of is okay, but it doesn't really solve the task of recommendation, especially personalized recommendation. You could like a painting by Picasso, maybe for a specific reason, that is one particular painting. It doesn't necessarily capture your true personal preferences. So eventually, with the arrival of deep learning, people start to use feature extractors like convolutional neural nets to learn representations that would look something like this. These were really good at capturing visually similar art pieces, but it was quite difficult because recommendations from CNNs don't really have direct interpretation, especially for human understanding. The other challenge is basically art is quite complex, as you can imagine. And capturing these complex concepts that are embedded behind the art pieces beyond the visual aesthetics is quite difficult, because you can think of reflections, cognitive reflections that are triggered as users actually interact with visual content. It's really subjective. It's beyond the visual aesthetics of the painting. So how can we actually drive this kind of recommendations which capture these hidden representations that are beyond the visual aesthetics? So this essentially requires understanding how do users interact with this kind of highly subjective content, and from which modalities can we actually capture these elements. So in a paper that we did back in 2023, we asked this question. So how can we learn, or how can a machine learn these kind of complex semantics that are embedded within visual art? So which are the modalities, or the elements, in other words, to actually drive recommendations? So we have images, we have textual descriptions. So the National Gallery dataset gives us this information about each painting. You have the visual image, you have some metadata information, and you also have semantically rich textual descriptions. So we have different modalities that we can actually exploit. So the first thing is, okay, let's try the classic approach. We trained image-based approach, and then we resorted to actually textual descriptions. So textual descriptions can be the actual documentation of the painting, what the author actually intend to communicate. It could also be from reviews of people about the painting. So this kind of captures the broader perception of users about each of the art pieces. And essentially, we used topic modeling techniques to learn this kind of semantic or latent semantic representations for the art pieces. So you have an image and you have a parallel textual description for each image. And we're trying to drive recommendations from these kind of semantic representations. And similarly, you can do the classic resonate approach as feature extractors, and then you end up with similarity matrix. So if a user likes this painting, we can drive recommendations from this. The central idea is essentially whatever technique you use to learn representations, you end up with some kind of vector space. In principle, similar paintings will be represented close to one another in this representation space, so from which you can kind of drive recommendations. So that's the underlying idea without going too much into the technical detail. So what we did was, okay, let's try to learn representations using all of these different techniques. So we have BERT, which is a transformer-based approach, a pre-trained model. So we used it to extract latent semantic features. And we used LDA, which is also latent rich data allocation. And ResNet is the image-based approach. So here, as you can see, we have the 2D representation of the learned embeddings. As you can see, these are like quite different representation spaces. So the kind of recommendations generated from any of these is completely different. Then how do we actually know which recommendation system works best at actually capturing these hidden semantic representations? And also, can we actually combine these recommendations? So we also did something called reciprocal ranking fusion. So this is basically combining recommendation from different models. So we end up with a lot of almost 9 different kinds of recommendation engines. And the ultimate judge is actually the visitors, or the museum visitors, or the users in this case. So we needed to run a user study to understand how these models perform at actually capturing these hidden representations of users. So let's see one example. So here is a target painting and a recommendation from one of the topic modeling based approach. So this is LDA. So look at the target painting, and this is the most similar recommendation. If the user likes the first painting, LDA would give you a recommendation of the second one. Looking at it visually, they look similar. I cannot see you, but I assume you would agree this looks like a good recommendation, right? So what is good about topic models is actually you can somehow try to explain the recommendation, we can go back into the topic distributions of each painting, and particularly they have similar distribution, and topic 8 is actually more prominent across this distribution. And if we unpack this and look inside, we can find these prominent words: Christ, saint, Jesus, I mean, you could tell this is kind of a religious context, right? So LDA kind of does a good job at actually capturing these kind of hidden semantic relationships between the contents. These are a couple of more examples from the other two Rexis engines. So BERT is actually also doing pretty much okay. As you can see, the distributions here are pretty much the same. And if you go inside and look at the words, they are also kind of descriptive of what you actually observe in the visual aesthetics. And the last one is ResNet, which is image-based approach. Basically tries to match visually similar content. And unfortunately, we cannot explain this like we did for LDA and BERT. But let's take a closer look at the ResNet recommendation. Visually, these two recommendations, these two paintings look the same. So if a user likes the first, recommending this one wouldn't be a bad idea. If you look at the visual aesthetics, they look pretty much the same. But if we go back and look at the documentation from the National Gallery dataset, the first painting is titled "The Time Ordering Old Age to Destroy Beauty." This was from 18th century by Bantoni. And the second painting is "The Donor" from the 16th century. You can already tell these paintings were painted far apart in time. And the description also tells us here the winged figure on the right side is actually depicting time. And the old lady is trying to disfigure the face of the young lady on the left side. So Bantoni is trying actually to tell us time is inevitable and beauty can pass. So this is the kind of message he's trying to communicate in this painting. So when we look at the description of, or the semantic description from the documentation for the second painting, this is Mary Magdalene, and this is the precious ointment. And this is more of a religious context. And this painting is actually found in the altarpiece of a church. So if a user likes the first painting, would you agree that the recommendation is kind of a bit off? Because there is clearly a semantic gap here. So visual similarity does not necessarily tell semantic relatedness or closeness. So it doesn't really work well for a recommendation system to actually match visually similar content. If it's in a different context, it would work with visual similarity matching, but for paintings, which are highly subjective contents, visual matching can be really challenging. It does a really good job at finding visual aesthetics, but semantics is really hard to capture. So this is pretty much what we observed in user studies. So you can refer to the paper to learn more about what we found. But we basically measured beyond accuracy measures. So these are measures to tell us how good is a certain recommendation engine, how accurate are the recommendations. Diversity essentially measures how diverse are the recommendations. So we give recommendations, not just one item, but multiple items. And sometimes users would like to receive a painting or an item which is kind of diverse. They want to learn something new they don't know before. And novelty basically captures this. How novel were these recommendations? Did you find something new that you didn't know before? Or how surprising were the recommendations? So if you can manage to strike a perfect balance across these four evaluation pipelines, the recommendation engine can be considered a good one. So now we observed from what we did with ResNet's textual recommendation and visual recommendation, okay, the semantics of an artwork can be captured both from the visual and from the textual representations. But can we jointly learn these two representations so that we have a more powerful model that can actually capture both hidden semantic representation, but also visual aesthetics? So in a follow-up work, we propose a transformer-based architectures which are called blip and clip. So without going into too much the technical details, So what these architectures basically try to do is learn early fusion from the two modalities. So we extract feature from both dimensions or both modalities, and then we fuse them at the feature level to generate embeddings or a joint embedding. And we use these models to basically drive recommendations like we did with the unimodal approach like Blip, ResNet, and LDA earlier. And then we did another user study. And interestingly, we could confirm that the early fusion approach works actually better. So Blip particularly performed slightly better than the other approach, the late fusion. So Blip, the bootstrapping approach, which is a transformer-based architecture, was actually quite good, and it's being used in many different applications for multimodal learning, for captioning. It's a very powerful state-of-the-art model, and it turns out for a recommendation task, it also captures both modalities for learning representations. So now let's come back to this recommendation task. So we have a user, and we want to drive a good representation, but we can do this using different techniques and drive recommendations that could actually strike a perfect or a rather good balance across these accuracy, novelty, diversity, and serendipity dimensions of user evaluation. So this is a screenshot of the web app that we did for the National Gallery. So now we managed to actually find the interesting items for users. But the recommendation service doesn't stop here, because you need to deliver the actual content. The contents are distributed across the museum in the physical space. So imagine a user have only 1 hour to visit the museum. How can we actually help the user navigate this? So we need to give a path recommendation. This brings a lot of problems and a lot of challenges from the physical space. First thing, some people are not tolerant to crowd. So even if you have an interesting painting that is recommended in a certain room, maybe the room is kind of quite crowded. So how do you actually navigate this and in the physical space? And for example, are the users tolerant towards walking too much to find interesting paintings? So this brings additional constraints, which I will not be talking about, but in this paper, we discuss something called multi-stakeholder awareness. So in the National Gallery dataset, for example, we have curators. They want to educate visitors about a certain theme, for example, monsters and demons. You have collections that are themed as women artists, landscape. So sometimes there are like themed exhibitions that the curators want to expose visitors. But when you do a user profile to drive recommendations in the app, the user profile doesn't really match with what the curators want to expose in that day. So how can you prioritize this? So it's like multi-stakeholder. You have a stakeholder on one hand, the visitor, and you also have the curator. So matching this is quite challenging. So it leads to a more complex optimization problem, trying to find the best trade-off in the physical space as well. Some venues might be closed, and there will be some rules in the physical space which users are known to be not following rules. So it is quite a challenging task to find actually a path recommendation algorithm, but I won't be talking much about this. So moving forward, so far I've talked about recommendation algorithms or representation learning, driving good representations from data, and then driving actually quality recommendation, which can be considered as good because of striking this balance across beyond accuracy measures. But what are these downstream applications? So these models have been used in the entertainment space, which is online recommendation of artworks, can be a physical space recommendation in an actual museum. But what about healthcare? So now I will be shifting into a completely different domain, but the underlying architectures or the techniques that I will be talking about remain the same. So we talked about cultural heritage, we talked about visual arts recommendation systems, but in healthcare, particularly in mental health care, what can be the potential applications of these systems? So art therapy, particularly in hospitals. To give you a little bit of context into the scenario, intensive care units or hospitals in general, their design is primarily focused on supporting medical activities. And in this process, the user or the patient's experience is often overlooked. these environments can be quite traumatic and could lead to potential harm afterwards, after being released, and patients can develop a condition called delirium, and specifically, which is diagnosable condition called post-intensive care syndrome. So I will focus on PICS, or post-intensive care syndrome, particularly a scenario, a situation where patients find after being discharged from an ICU. So research actually indicate that 80% of patients released from ICU suffer from this diagnosable condition called PICS. And this leaves a long-term impairment, which could last up to 5 years or more on their physical, mental, and cognitive abilities. Particularly, the mental health toll could be characterized as anxiety, depression, even PTSD. And there was no actually formal intervention for PICS until a few years. So patients are usually advised to follow through psychotherapy, which could, on average, take almost 78 weeks, not to recover, but to start seeing significant improvements. But in literature, there is a well-documented evidence that therapeutic effects of visual exposure to particularly nature as positive distraction is really powerful. For example, the movement of cloud, the sunset changing its color, the greenery exposure of nature has a strong link between well-being and nature. And patients actually have been treated previously for delirium or for PTSD by being exposed through nature-based art. And a colleague of mine recently, back in 2023, were exploring during her PhD an intervention mechanism using digital nature for post-intensive care patients. So the approach was basically giving patients as a preference elicitation a set of paintings that would help them recall their illness, and then they will be given a guided meditation or a guided session through helped through visual arts, which are recommended to expose them to healing concepts. So what's the challenge here? So the challenge here is basically patients have unique ICU experience. So not all patients can actually resonate to the same piece of art. And the other challenge is therapists or clinicians who can actually deliver this treatment, they have limited knowledge about visual art, and the search space is actually quite large. So it's quite difficult for them to actually find those relevant paintings for their patients. So what we did was, okay, can we use a visual art recommendation system that we developed for actually entertainment in the museum to drive therapeutic recommendations? So what we did was we designed pipeline for art therapy. As you can see, these models are basically pretty much the same models that we used earlier, but the pipeline unfolds slightly differently from the classic museum-based recommendation. Of course, we have a preference elicitation phase where former ICU patients will be exposed to a piece of art where they kind of reflect on, which can be used as an input, what the user like. Basically, it's a user model. And then we generated recommendations using these models. And we ask also therapists actually to do the same thing. And we can see if recommender systems actually work better or can actually do comparable compared to the experts approach. And then we actually plugged in back the guided therapy session and we collected some relevant measures. But before we actually deploy these services, we need to ensure safety, because some content can actually be dangerous or could trigger some bad emotional reflections. So to safeguard against this, we did some pilot tests with experts. So we have 4 experts in affective design, ICU research, and also some nurses involved in treatment of post-intensive care patients. Basically, what we did was we gave them some recommendation from each of these engines, and then they kind of gave a rating and also reflection on each of these. And this table kind of summarizes the results. So as you can see, the resonate, the visual approach, was kind of preferred over the text-based approach. And if we see some examples from the LDA engine, for example, this was a recommendation from LDA. There were some runes in this picture. which is kind of distracting and which is not really advisable for art therapy. This was from experts too. And another example from BERT is this one, which kind of has a storm, and it's not really recommended for patients struggling with trauma. So there is a very high risk at deploying these systems directly into a therapeutic pipeline. So what we did was we did an initial intervention to just filter out those contents by therapists, and then we deployed the services. And we did some evaluation with almost 200 patients on this paper, I believe. And we measured additionally immersion and engagement. So immersion and engagement are quite interesting aspects, especially when you are doing a guided art therapy. How relevant were the contents in terms of immersion and engagement? And as you can see, the Rexis engines perform quite better in some cases and comparable with the expert recommendation. So also in the PANAS, which is positive affective and negative affective schedule measuring, before and after therapy, patients have shown significant improvement. And we recorded actually almost a 15% acceleration in recovery of the patients. So this was quite encouraging to see that Rexis, which were designed for entertainment, could actually play a role in helping the therapists save their time and finding those content that were actually relevant for unique needs of patients. But is it good to actually rely, now that we know Rexis systems, they work better? Can we replace the therapist? Of course not. We've seen that there are some risks involved. And then in a follow-up work, what we suggested, okay, we need to use Rexis for sure, but we need to put human in the loop. So that's what we basically did. So we developed these systems, we put human in the loop, and then there is a feedback loop between the Rexis and the actual therapists. And once only validated by a therapist, recommendations can actually go out to patients. And the study, actually a follow-up study, actually shows some interesting insights. So patients gave some reflection and we did some sentiment analysis. And interestingly, the multimodal engines, particularly Blip, was performing really well in terms of user reflection. So there were no negative reflections from users from this category in the multimodal sentiment analysis. And there were also some interesting findings from reflexive thematic analysis. Basically, we were trying to see what healing concepts were actually extracted through the recommendations. And as you can see, rejuvenation, hope and purpose, engagement, safety, more positive healing concepts were extracted through the use of these recommendation engines. So what is the potential? So post-ICU, we were able to help patients recover faster. But can we actually bring this to the ICU? And what you see here is Vital Sky, which was developed by Philips. So the next step is actually to bring this in the ICU and solve this problem from the source. But it also has other implications. We can use this intervention, for example, in hospital environments where we can consider more traumatic or could put people at ease. So it could be during MRI checkups in different hospital scenarios, which are designed to basically prioritize medical activities. We can think about user-centered design to introduce art therapy or visual exposure to nature-based content in these environments. And another potential application would be, for example, in residential care, using this device, for example, called Ambient Echo. So this is a residential care, self-administered care for patients who are at home, discharged, but not necessarily recovering from peaks, but also it could be anyone who needs a mental health refreshment can benefit from these systems. So if you're interested to know a bit more about the techniques and the approach, this is the first paper we published at CHI with my colleagues. So you can scan this QR to find the paper, or it's called Artful Paths to Healing. And the follow-up paper is the AI Therapist Duo. You can find both papers, and we talk more details about the foundation models that we used, and then the techniques used to actually safeguard and more technical details. And so this is where actually the ArtAICare concept was founded. And we are working in collaboration with the Federation of Art Therapists in Europe and the Luxembourgish Federation of Art Therapists. So what we have is basically we have an application which serves basically as an intermediary between patients and art therapists. So we have recommendations for both therapists and for patients. The primary approach is basically the visual exposure therapy, but the recommendation system is really at the heart of everything we do. We also have this thing called immersive expression therapy, which we use VR environments using MetaQuest. So patients can actually immerse themselves in not just view a painting or a nature-based content, but they can actually immerse into a scenery which is recommended by one of these models, so scene recommendation, and they can interact, they can reflect, they can find themselves in an environment which is soothing, comforting, and therapists can actually help them reflect. Sometimes trauma can be hard to verbalize, but art kind of opens a creative medium of expression. So in the virtual canvas scenario, patients can actually draw on the walls to reflect themselves. And we have models that can actually analyze the drawings afterwards and give some recommendation to therapists' dashboards. So there is also this thing we call virtual co-creativity, meaning you can enter in a joint session with different patients and you can interact. And we also have these AI agents that assist in the creation of art and in the therapy session. But always we involve registered therapists. So if you go to beta.artaicare.com, you can have a free trial. But if you want to actually use the service, always you need to be involved or partner with a registered art therapist. So there are like interesting areas that we are also exploring. Currently, we are exploring this space called cross-domain recommendation. This is a paper under review, by the way. So what we are trying to do is, can we actually use music therapy as also a profound space which is successful in treating people with mental health issues? And we are currently using for preference elicitation visual exposure or visual stimuli, but music also have a unique way of exploring or exposing people's emotion. So we try to use music also as a way of preference elicitation to drive therapeutic art recommendation. So this is what we call a cross-modal recommendation for art therapy. So overall, these recommendation techniques, whether it is a content-based, unimodal, multimodal, or cross-domain recommendation systems are really at the heart of what we do. And not just for entertainment, but they have really significant value in real-world applications like mental health care. And I hope this kind of gives you an overview of the content-based approach in the entertainment space and also in a completely different area, which is mental health support. So I will close by quickly talking about a few challenges and issues in the broader recommender systems pipeline. So some areas where we can work on is essentially, okay, now we have these black box models, whether it's unimodal, multimodal, cross-domain. What the user see is actually, the user gives their preference and how much they like a certain item. And then under the hood, this is a black box for the user. We just give them a recommendation and they consume. But these are black box. Can we actually give users control? And this is another study that we did. You can find in the multi-stakeholder approach paper that I mentioned earlier. So we were exploring how can it help actually to give users control? So this algorithm design is especially giving users hyperparameters to control actually different aspects of recommendation. For example, sliding this eta parameter can actually play with the diversity of the recommendations, the popularity of the recommendations, different facets. For example, diversity could mean time period, diversity could mean layout, it could mean different things for different people. So giving users more control can actually help them find more interesting items, or also build trust more on the recommendation system. So this is what we are currently exploring. Can we give users more control in research? Can we give users more control of what they get instead of just give me your preference and I give you a recommendation? I think this is something that you like. So we think users deserve the chance to actually dictate what kind of recommendations they consume instead of having a black box. But modern recommendation systems that rely solely on this neural network or deep learning approach kind of makes this more of a black box or a gate to unpack preferences. And one of these research areas that we are exploring in the multi-stakeholder awareness, also user controllable recommendation, is essentially driving algorithms, designing algorithms with hyperparameters that can be adjustable, that can be controllable by users to somehow shuffle recommendations content. And the other thing that I would like to mention is explainability. So can we explain recommendations? What is actually the impact? So we've seen that explaining recommendations, for example, in the scenario that I mentioned earlier with LDA, it was useful to actually go back into the topic model, actually see why is this model giving me a recommendation? Because these two paintings have similar semantics. They are both religious. They have the following list of topics involved in them in their description. So another example, what everyone can find is Netflix. So I'm not sure if they are still doing this. Is a screenshot I took a few years back, but you can see, like, because you watch shows with sharp humor and strong female leads, we're giving you this recommendation. So you can clearly tell there is a semantic analysis of the content, not just the metadata or not just the visual aesthetics or the movie content. So if you have exposed yourself or watched or clicked on a content that has some kind of dangers, then Netflix might give you a recommendation. And I find it useful. I don't know about you, but I find it useful why I'm getting this kind of recommendation. Did I actually watch this kind of content before, or does this actually make sense? So explanation is also a very interesting concept that plays a huge role in driving recommendations and also in driving the acceptance rate of users in the recommendations. And finally, this is something I would like to talk about. Maybe this would be a good topic to discuss afterwards, echo chamber. So recommendations today, they try to collect information about what we like, and they basically inject back this information. So we get back ourselves or our reflections in our recommendations, our social media feeds, our products, the services that we consume from pretty much any platform tries to push this kind of recommendations that are basically learning what you like. But doing this kind of puts us in a bubble, which is filterable, limiting our exposure to diverse perspectives, and could also potentially reinforce existing biases and stereotypes. So my final conclusion or my final message, you could disagree, arguably, but is recommendation systems should not make our world smaller by putting us in a filter bubble, but I think they should make it bigger by exposing us to contents that are new for us, that are potentially good for us, that we might even learn to like in the future. So yeah, this is pretty much what I have to share for today. I hope I am right on time, and I think we could do a few minutes of Q&A. So yeah, thank you.